The classic Gauss's law example. Anytime, well, we might start here. Anytime you have a non-point charge, and you're not far enough away to treat it like a point charge, Gauss's law becomes the limit of accessibility. Because if you try to calculate individual point charges or individual DQs over large quantities, if you can't integrate the DQs, then it just becomes hell. You know, right? A bunch of 30-point charges. Calculate it for 30-point charges. Yeah, not so good. But the arrangement has to be just right. Consequences, though, are oftentimes surprisingly helpful. So, by the way, I wrote over here sort of the basic approach, and I put it off way off to the side, but this is the application strategy. So you always want to do this when you can. Establish your Gaussian surface. Specifically, look for regions or surfaces where the electric field is zero. That's kind of nice because even though it's a surface that's part of the enclosure, you don't have to do anything in that. You don't have to calculate anything. You already know the flux is zero in that region. Or when the electric field is constant, and I should have put an arrow over here, with respect to its magnitude, but also orientation. Because you want to be able to define an EDA over a nice, useful spot. By the way, it feels so much cooler in here. You notice that? They fixed it.
Finally.
Of course, you can't tell if they fixed it or not. That's a backhanded statement, right?
It's also cooler outside.
Exactly, that's what I mean. You couldn't tell if it would feel like this even if it didn't work. But the guy did come in this morning, which is why the door was locked. So just so you know, you always come in and unlock it, but the guy was in here this morning, so there you go. Okay, so let's look at some non-simple examples of what it might mean. Okay, so let's look at let's look at a solid sphere. And I'm going to make it a solid conducting sphere. The only reason I want it conducting is this will allow me to know where the electric charge is. Where's the electric charge? A conductor means what? The charges can move. If the charges can move, where are they going to go on a sphere? They're going to push themselves to the outer edge, kind of like a bubble, if you will, or it's sort of the lowest energy location where they can push apart from each other. Lowest electrical potential energy, if you will. So, plus or minus, so whatever the value is, the charge is going to be out here somewhere. And there's going to be some total Q now, right? And that's going to depend on how many electrons have been yanked off this thing. So this is going to have, it'll look something like this, right? Solid, but it's a sphere. Now, there's two defined regions here. You got inside the sphere, and you got outside the sphere. So the question is, what is the electric field inside or outside the sphere? Well, let's start with inside because that's sort of a nice, comfortable place to start. When it gets cold outside, we go inside. So let's look in the friendly location, and let's start by, there's the center, and this thing has a radius of r. So we'll start by asking, what is E inside the sphere? And by that I mean when r is less than the radius. Gauss's law makes this a trivial example, actually. We've got a sphere, so the defined Gaussian surface, because it's spherical, use a Gaussian sphere. So I'm going to say a concentric sphere, because we're looking at a sphere, so basically a sphere at the same center as the charged sphere itself. So there's my Gaussian sphere. And the radius of this thing is r. So if I want to know what the flux is, I'll calculate that. Because of the spherical symmetry, I can say that it's going to be equal to E times A for this Gaussian sphere. And just because we have big R and little r, I'm going to put, it's the area at this distance r. For this particular, and I don't know if it's helpful, but I'm going to say it's the electric field at r as well. Because of the symmetry, whether I'm here, whether I'm here, whether I'm here, at all places, the orientation of dA and E will always be the same. And as long as I'm along this sphere, the magnitude of my electric field with respect to the surface area will also be constant. Got no reason for it not to be, because no matter where I am, I'm the same distance away from the closest charges and the farthest away charges. So I've got the symmetry there, regardless of where I am. Okay, so at any particular point, I've got E at a distance r being related to 4 pi r squared, whatever it is. I don't have to integrate this. And according to Gauss's law, then, E flux, and I should change colors here now, since I'm coming to some resolution. So that total flux, which is in fact ER 4 pi r squared, that should be equal to the amount of Q that's enclosed divided by the epsilon naught. I've already done more work in this problem than I probably should have. All of the charge is outside. I got no charge in the center. If I've got no charge in the center, this is 0. If my area is not 0, but the product of these two is 0, the requirement is for any distance r that is smaller than the radius, in other words, as long as I'm inside, this quantity has to be equal to 0. Now we could figure out a different way to solve this. And Ivan was in my office and we were talking about this the other day. We could in fact take some point here and calculate Coulomb's law over every internal region, over every charge along this outer surface, right? We could do that. But it's not particularly simple to do. Because at every point, you no longer have spherical symmetry if you're looking for this compared to this, compared to this, right? There is a way that rationalizing it, the bottom line, is whenever you have a uniformly charged sphere, and Gauss's law is just the easiest way of establishing this without having to do a deep calculation. The electric field is 0 inside. Now, just to make it clear, in the process of charging this sphere and removing electrons, there will be a transient interval where the charges take time to arrange themselves and push them out as far away as they can. During the time it takes for the charges to, in fact, distribute uniformly, during that little flux, if you will, during that movement, the electric field is not 0. But once everything settles, it is. Okay, so the key is this assumes that you have a static charge sitting somewhere. This does not assume that you've got a moving charge floating around, because the flux, the calculation will become more complicated potentially. At least with respect to where these charges are distributed. Okay? So that's very important that we're only looking at once the charges have settled. It would still work for a point charge, but you have to wait for everything to settle. That'll be important when we get to electric fields for conducting charges in a wire. Okay, you do have an electric field in a solid wire when you have charge flowing through it. But this is not that condition. Okay. Charges are spread out and they stop moving. Now, so it's kind of pretty straightforward and easy when you step back and look at it. Now let's think about this for a second. If we're outside here somewhere, okay, let's put ourselves now outside of the same sphere. So, in this case, R is greater than R. Well, we're out here somewhere. I'm not going to go very far away. I'm not going to cop out and say I'm so far away that R is small compared to the separation distance. Okay? I'm not going to do that. I want to know what this distance R right here. Now, can you see maybe the challenge of calculating the electric field for all of this stuff here? Can you see why that might be tad problematic? The nice thing, though, is that as long as I stay at that same radius or that same distance away, I can still take advantage of spherical symmetry. Because no matter where I am, the relative position of the closest and the far away charge is going to be the same here as it is any other point, because they're being uniform. If they're not uniform, then all bets are off. But as long as they're uniform, I can save it. So again, I'll use a concentric sphere. Same sphere, only now R is bigger than the radius. So well, we play the same game. I don't even have to do a whole lot of calculations to this. The area of this sphere now is going to be 4 pi epsilon naught, or no epsilon naught, I haven't jumped in there, R squared. And the total flux, which is going to be E a sphere, I better say, E at that distance R away. Don't forget that I'm talking about that. If I need to space that out, I do that infuriatingly. Again, I don't have to deal with any angular concerns because I've picked a region where, or I picked a way where I don't, it all simplifies out. It's a good thing. This quantity is going to be equal to Q enclosed over epsilon naught. So if I solve for E, for any given sphere, I'll be a certain symmetric distance no matter where I am around the charged sphere. And I'm left with Q over enclosed over 4 pi epsilon naught R squared, as long as R is greater than R. So in this particular case, even a charged sphere reduces to a point charge. You don't even have to be close or far away for that to be the case. That's kind of nice. So now we can put numbers in there and we can solve, we can get a value for it. So again, it does reduce to Coulomb's law. And more specifically, I'm not going to write the extra details, but if you want to write another line, then you could also note that the vector is going to be radial away. So there you go. That's those are the easy applications. Now let's look at another application that isn't necessarily so easy. Well, actually, even before we do that, let's change this and let's carve a hole out inside. If I took the same charge and put it on a hollow concentric sphere, where's all the charge going to flow to? Still going to flow to the outside shell. Regardless, it's still going to push outward. Which means, without even doing it, if I have a hollow sphere, the electric field is still zero inside it. That electric shielding effect is oftentimes why we surround our sensitive electronics in metal devices. Because we can shield the electric field outside from what's inside. And even if you have small changes in the charge due to external fields, they have a smaller effect in here than if you didn't have this shield around it. Okay, so when you're inside an aluminum building or a metal building, the more closed the building is, the harder it is to get a cellular signal or a radio signal. That's the electrical shielding effect. If you're outside of it, it's just like there's no difference between this and any other charge sphere. So I'm not going to write that stuff, but that's sort of the consequence. Now, here's one that's kind of interesting. This actually has a gravitational analog. I'm going to keep these because we still have to calculate that. Let's change this. Now again, you can put some numbers in there, and I hope it's not painful that I'm not putting extra numbers in. I don't think there's so much with this if you've done. Here's an example worth considering. If you have a uniform charged insulator, sphere, and to make it even funner, let's make the charges negative. So this is, I don't know, not a semiconductor, but this is some insulating element that doesn't allow charge to flow, plastic or something. And inside there is embedded some electric charge. Basically, somehow as you deposited this and created this, you've somehow used charged ions in the formation of this thing. So we've got extra electric charges in there somehow. Okay? And we'll assume that they're uniform. And again, we'll make it a radius r. So we're just looking at this particular sphere. So this has a radius of r, and there's some total charge q. And let me add that. So q total, for this one I'm going to give a number, and it may be useful at some point in the calculation. So maybe 5 times 10 to the negative 8 coulombs. I don't know if it'll help me not having a total charge there. Okay, so if I'm in the center, and I'm some distance away from the center, maybe I'm out here somewhere. And a distance r. What's the electric field here?
Q enclosed over.
Well, first of all, we would play the same game and choose a Gaussian surface with the radius r. Because of symmetry. If it's a sphere, use a sphere. Now we got a slightly different problem. Because the electric field, or the flux, is related to E sphere. Again, I'm going to make the assumption I don't have to recalculate E in terms of A and do an integral because of the spherical uniform symmetry. This quantity is going to be equal to Q enclosed divided by epsilon naught. But we got a problem here, or at least we have a new consideration, because there's charge inside here. It's no longer, put more of these lines in there. It's no longer 0 inside the sphere. So now I got issues to deal with. So we'll note, we know what the area of the sphere is, but let's just note that Q enclosed, that's how much charge is inside this thing. And that fraction of charge, we'll write it this way. We're going to have to figure out a separate way to get it. One way might be to say that it's the ratio of the total volume. If I want to calculate Q enclosed, I would take the total charge Q, but compare the ratio of 4/3 pi r cubed to 4/3 pi big R cubed. In other words, it's this fraction of the total volume times the total amount of charge. Okay, if the charge is uniform, it's spread out over a certain volume. If I've only got 25% of that volume, I'm going to have 25% of the charge in that volume. So we just sort of rearrange this. A lot of this stuff comes out, and we're left with Q total, R cubed, divided by big R cubed. That's Q enclosed. So now we play the same game. Maybe life will get happy, maybe it won't. But if I solve for ER, first thing I'll do is I'll note that I've got 4/3 R squared is the area of my sphere. And that multiplied by E is going to be equal to the total charge of the sphere, R cubed over R cubed, big R cubed. And I need an epsilon in there. So if I were to solve for ER, divide both sides by 4 pi r squared, and I'm going to be left with Q total R cubed over 4 pi epsilon r squared, excuse me. I'm just going to put everything in here before simplifying it. I get all of this stuff, which reduces to Q total times R times 4 pi epsilon naught R cubed. And I'm going to separate everything that's constant from the one variable, which is where am I in this thing. By the way, again, I can play the same thing and say in the distance that the direction of R is going to be radial with respect to this. So I'm just going to go ahead and put that in there. Actually, I probably should have done that. Write it in a separate line. If I don't, so I'm going to simplify it and say this is Q total 4 pi big R cubed, and I've got R in the direction of R hat. Okay, there's my vector. If Q total is negative, then it just means it's pointing inward instead of outward at this particular location. So think about this for a second. As R gets smaller, starting at the outer edge, and you move to the center, the electric field goes to 0. It's 0 at the center because you've got equal charges all the way around it, and if you will, no enclosed charge. But as you move further and further out, the electric field increases with R. Until you get to big R, and then it reduces to a little charge. When R becomes big R, then this reduces to Q total over 4 pi epsilon naught R squared. It's kind of cool.
I think your epsilon naught's missing out of that.
Is it? Oh, I'm sorry. When I rewrote it over here, I left out my epsilon naught. I'm sorry. That's why I try to, especially with my other class, I try to emphasize fewer steps, because the more steps you physically write down, the more likely you do somehow. Manufacturing processes the same way. In chemistry, you put everything going to work right next to you, because the more you go one side of the room to the other, the higher your chance you're going to spill. So it's, practical. But is this surprising though? Your electric field decreases from whatever it is here to 0 at the center. If I were to plot the electric field magnitude as a function of R, it would look like this. Now, let's think about this for a second. Coulomb's law we talked about being very similar to a different inverse R squared law.
With gravity.
Gravity. With gravity, we have a nearly uniform mass spread out in a solid fashion. As you dig inward, gravitational force, gravitational acceleration decreases. Well, it makes sense when you get to the center, there's no gravitational force because you're being pulled equally in all directions. But it linearly decreases with depth as you go towards the center of the Earth. So it's analogous to the uniform distributed conductor, or insulator, charged insulator.
So, if we were to suppose that heat wasn't an issue, and we dug a hole in the center of the Earth, you could jump in, and you would just stop and float at the center.
Absolutely
and
not.
not be harmed.
Absolutely not. It would look like a spring. It would be like an elastic force. Because you've got an acceleration. Remember, let's write the analogy for gravity. So I think this is one of those cool places where you can just apply. What might Gauss's law for gravity look like? Think about this one for a second. What should gravity look like for Gauss's law?
I'm with you.
And we'll use this, it's a little simpler to talk about. These are where the symmetries come in and where some weird things you start thinking about that you might not otherwise even be able to know. So here's the Earth, and it's a solid uniform mass. The mass acts just like electric charge, so it's what produces the gravitational force, similar to electrical force with electric charge. Well, the gravitational force, when you're outside, when you're treating point charges, it looks like some constant times the mass, if you will, of the Earth times the mass that's near the Earth divided by R squared. Okay? What would the flux look like? What would the gravitational field look like? If I divide both of these by the mass in question, there's my gravitational field. G as a function of R is going to be equal to whatever this big G is times the mass of the Earth, that's the total mass now, divided by the square of how far away you are. This would be the vector G. It isn't always constant, it's only constant when R doesn't change by very much. Right? So moving a few miles, when you're 1,000,000 miles away from the center, it's nominal, it's negligible, doesn't change much. However, what if we replace this with an equivalent A? Here's the center. I'm probably being more esoteric than you want me to be. Let's look at this distance away from the center of the earth. Say I could dig a little hole and get right in here. What would the gravitational field be there? Well, if I wanted to replace this by A, one thing I might do is I know the area of this thing is going to be 4 pi r squared. So if I multiply by 4 pi and divided by 4 pi, now I've got the area of that sphere. So if I just rearranged it, what I'm left with is G